Hello everyone. Thank you all for joining the CPAS conference this year and listen to my tutorial slides. Before I start, I wish you and your family members are safe and healthy this year. Today, I'd like to give you guys an overview of the recent research progress on the modular-based high-frequency power electronics in high-power applications. When I mention high power, I'm talking about tens of kilowatts to range of megawatts applications. This page shows a popular way of displaying the high-level overview of the power electronics applications. The x-axis is the voltage rating and the y-axis is the power rating. Based on the voltage rating, we can clearly categorize the applications into low voltage, medium voltage, and high voltage applications. According to the IEC standard, below 1.5 kV DC or 1 kV AC, it's considered as a low voltage. Between 1.5 to 30 kilovolts is a medium voltage range, and beyond 30 kilovolts is the high voltage area. The high-frequency power electronics dominates the applications in the low-voltage space, including the switching mode power supplies for electronics, telecoms, and information technologies industries. The power rating of these low-voltage applications are a few watts to a few kilowatts. Recently, there are many emerging applications like EV charging systems, traction drives, and energy storage, with the voltage ranging from a few hundred volts to over 1 kilovolt, and the power ratings can reach to a few hundreds of kilowatts. Around 1 kilovolts and up to 1.5 kV, there are lots of power electronics inverters for renewable energies, like PV and winds. And some of the inverters reach the medium voltage range, like a medium voltage wind converter. The power rating in these grid applications can ramp up to megawatt scale, and in the medium voltage range, variable speed drives and propulsion drives are the major applications, and the power rating can go beyond tens of megawatt. And in the high voltage area, fax devices like a STATCOM and the HVDC converter stations are the major power electronics applications, and the power ratings can reach gigawatt level. So there are a lot of high power applications for the high frequency power electronics technology to penetrate, and AC/DC type power conversion system are the dominating applications in these high power areas. The recent trends in many of the emerging applications are moving toward higher power and higher voltages. For example, the traction drive and onboard charging system are moving from 300 volts to 1 kilovolt, and the outboard charging system peak power can reach hundreds of kilowatts to even megawatt level. In addition to the secondary side power distribution, the power electronics are penetrating into the propulsion side in aircrafts with much higher power levels. Therefore, the electric systems are moving toward 1 kV or even medium voltage level, and the propulsion power we are talking about is easily over megawatt level. Battery strings in a utility energy storage system are reaching over 1 kV with a megawatt power scale. In the large ships, the electric power distribution and propulsion system is already over 10 kilovolts. In the power grid, there are active discussions of adopting medium voltage high power inverters for the PV and winds. All these trends come along with the accelerated adoption of the wide bandgap power semiconductor devices, especially the silicon carbide MOSFETs, and the power electronic circuits running at high switching frequencies for better performance like fast dynamic and frequency response, smaller footprint, and higher efficiency. So when we talk about the high frequency power electronics in high power areas, modular approach is gaining a popularity. Modular approach basically aligns with the concept of the power electronics building block, PEB, which basically a unit with integrated electrical, control, cooling, or even the filtering functions. Modular approach basically uses these identical modules to build up the power and voltage. This allows a faster development and qualification cycles, very suitable for the recent emerging applications with very different requirements. This also reduces the development risks when using the high switching frequency semiconductor devices like silicon carbide MOSFETs. The modular approach can dive down to the stack level, which are the integration of the semiconductor devices, monitoring, and the gate driving units into a higher power and higher voltage switching unit, or to the subsystem levels like MMC submodules, and all the way to system level like paralleling drives for higher power motors. Modular approach also reduces the technical barriers to reach medium voltage and high voltage levels. There are two major ways to reach higher voltage. The first approach is the direct coupling of modules. The most famous example is the MMC converter, that hundreds of identical submodules are stacked to reach the high voltage. Another example is to stack the devices, like IGBTs and IGCTs, which can be found in many medium voltage drive systems. Another way of reaching high voltage is through the transformer couplings. The most famous example is the Robinson medium voltage drive, of which a multi-winding transformer is used to realize the chain-link type H-bridge converters per phase. Robinson drive was invented in early 90s and is still the most popular medium voltage drive solution nowadays. Another example is the solid-state transformer-based converter system, which is using a high-frequency transformer for stacking up the power electronics modules for medium voltage and even high voltage applications. This is the outline of the tutorial. The first section is about some topology exercise. I'd like to talk about the popular modular multi-level converter, MMC, and move on to the hybrid MMC concept, followed by the benefits comparison in medium voltage and high voltage applications. In the second part, I'd like to talk about the modular-based resonant-type high-frequency solid-state transformer, including the converter and transformer designs. The third part will discuss about medium voltage silicon carbide MOSFET in series and its voltage balancing control approach for medium voltage high frequency operation. Lastly, the design of a high frequency auxiliary power supply system with a medium voltage insulation capability and the low coupling capacitance will be discussed. The slide shows several popular conventional voltage source converter topologies for high power and medium voltage areas. Two-level design is the most popular approach due to the simple structure. To reach higher voltage, three-level NPC solution is very popular as well. Other popular three-level solutions are ANPC converter, NPP or T-type three-level converter, and flying capacitor-based three-level converter. To reach higher voltage level, there are two ways. One way is to stack up the devices in three-level structure, and another way is to use five-level topologies, like a five-level ANPC and five-level NPP. These topologies were dominating the medium voltage space for years. Therefore, the straightforward way for reaching even higher voltage is to try 7-level, but the commutation loops are extremely complex as well as the modulation methods. In 2002, MMC converter came along, which presents a completely different design concept. MMC is a 100% modular-based approach, and people just need to stack up identical modules to reach high voltage. MMC is very successful in the VSC-based HVDC market. Although it needs large number of devices, it still gains market share in high voltage and even medium voltage space. Basically, MMC fundamentally changed the way to build medium voltage and high voltage converters, significantly reducing the technical barriers. And it also adopts the wire bonding type IGBT modules in HVDC space, which in the past would be considered as a crazy idea. Not only in the HVDC space, MMC also has put its footprint in the medium voltage areas. This page shows several commercial examples, like medium voltage variable speed drives, STATCOMs, and MVDC technology for renewable energy grid integration, with the voltage ranging from 10 kilovolts to 30 plus kilovolts, and the power ranging from multi-megawatt to hundreds of megawatts. There are tons of papers available talking about MMC operation principle. This page shows the very high-level concept. The MMC phase lag is compressed of two arms, lower arm and upper arm. Each arm contains several MMC submodules in series and a reactor for current regulation. The total arm voltage needs to follow these two equations shown on the top in order to synthesize the AC voltage. It clearly shows that both upper and lower arms need to produce DC voltage with a low frequency AC voltage ripple. Similarly, the current that flows in the upper and the lower arms will contain DC and AC current as well. The right-hand side shows an example of MMC with 4 submodules in each arm. In this case, you can produce a 5-level phase-to-neutral voltage. If MMC submodule is a hybrid type, the total number of devices will be doubled compared to the 2-level topology. And if the submodule is a H-bridge type, it will be 4 times. Also, the total voltage rating of each arm has to be full DC voltage. The control of MMC is quite challenging and involves multiple control objectives. The arm voltage and output AC current are the primary control objectives. To achieve these goals, the control needs to create the voltage command for each MMC submodule. The control of MMC needs to also balance the total capacitive energies in the upper and the lower arms. In the MMC phase lag, the circulation current that flows inside two arms is a unique control freedom that doesn't exist in the conventional multi-level converter. Circulation current in each phase lag can be controlled to balance the energies between arms and also between the phase lags. Each submodule capacitor energy can be balanced through the PIM modulation and throttling methods by controlling the bypass time of each submodules. The harmonic current can be injected in the circulation current to control the total energy ripple in the arms, so that the voltage ripple of the MMC submodule can be controlled and even reduced in some extent. Another way is to let the MMC produce a common voltage to change the energy ripple in the MMC arms. In medium voltage drive applications, these methods are used to control the submodule capacitor voltage ripple at the low speed, high torque conditions. But these methods come with a penalty leading to limited output current capability and lower efficiency at the low output AC frequency. So MMC has a limitation of running at the low speed, high torque motor drive applications. So here is a short summary of MMC converter. MMC has three major advantages. First, it can produce a high-fidelity multi-level AC output voltage due to high number of low-voltage submodules. Each submodule doesn't need to operate at a high switching frequency. In HVDC application, MMC submodule can just operate around a few hundred Hz. Second, the modular approach significantly reduces technical barriers to build medium voltage and high voltage converter. Third, the high flexibility and reliability come with the redundant submodules, so the converter can be easily and quickly built for various power and voltage conditions. However, on the other side, MMC is not perfect. It also has many disadvantages compared with the conventional multi-level converters. First, it needs a high number of low-voltage devices, leading to much higher conduction losses, which is a very critical aspect in the HVDC application. If using the full bridge submodules, the conduction loss will be even doubled. Second, each submodule is very bulky as a large capacitor is required to absorb the ripple energy. This makes MMC a bulky and heavy solution for medium voltage applications. The third reason might kill many commercial competitions as the cost is relatively high due to large number of devices, gate drivers, control electronics, sensors, and submodule overhead costs. The last issue for MMC is its limited power frequency operation range, leading to reduced capability in the motor drive applications. So with the understanding of both pros and cons of MMC compared with conventional multi-level converter, the question here is, can we find a solution to balance the benefits from MMC and the conventional multi-level converter? If possible, we'd like to meet the following requirements. We like to replace the MMC low voltage submodules by simple high voltage switches for higher efficiency, smaller footprint, and lower cost. We also want to keep the same output power quality delivered by the MMC converter. Then the high voltage switches need to operate only at the line frequency for ease of device stacking and high reliability. If we can meet these three requirements, we might be able to find a better solution. So let's start with the most basic two-level topology first. It only has two switches, very simple. And if we replace these two switches with the chain link structure, we basically created the MMC phase lag. So MMC can be considered as a two-level structure of using chain link. Now let's take a look at the three-level AMPC topology. There are totally 6 switches per phase. Based on their locations and functions, we can categorize them into 3 groups of devices. Green group that is connected to the DC bus, purple group that is connected to the neutral point, and the blue group that is connected to the AC terminals. By following the same idea, we can use chain link to replace one of the 3 groups of devices. Then we can create 3 different types of 3-level version MMC converter. We just name it as the hybrid modular multi-level converter, as it is the combination of the 3-level topology and MMC solution. To meet above-mentioned requirement in the previous slides, the high-voltage switches in the HMMC has to operate at a fundamental frequency to reduce the operation risk and improve the reliability. All high-frequency switching actions are allocated to the low-voltage MMC submodules. So this is how we created the HMMC concept. The switching state of 4 high-voltage switches aligns with the AC output voltage polarity. When the phase lag needs to produce a positive voltage during the half cycle, Q1 and Q3 switches are turned on. The chain link arms are then connected across the positive DC bus and the neutral point. The upper and the lower arms can be controlled to produce the required AC voltage like the way MMC operates. When the phase lag needs to produce the negative voltage during the second half cycle, Q1 and Q3 switches are turned off. Q2 and Q4 switches are turned on. So the chain link arms are connected between the neutral point and the negative DC bus. The corresponding upper and lower arm voltages can be expressed as shown in the equations. There's a special switching state that Q2 and Q3 switches are turned on, and the upper and the lower arms will be in parallel. This state can happen when the AC voltage is zero crossing. Based on the operation, we can draw the required arm voltage and compare it with the MMC. For MMC, each arm needs to produce the voltage up to full DC voltage, but the arm in the HMMC needs to produce half of the DC link. This simply means that we can eliminate 50% MMC submodules in the HMMC converter, leading to footprint, number of devices, and cost reductions. As we can control the arm current, we can also control the current flowing to the neutral point. For a three-phase system, the neutral point of the three phase legs are tied together. The total current that flows into the neutral point can be controlled at zero all the time due to the balanced energy among three phases. As such, the two capacitors on the DC links can be very small and only serve as the commutation capacitors to provide the current commutation path during the switching state transition period. These small commutation capacitors also protect the high voltage switches if they lose the control signals. This is very different from the conventional three-level converter, as large split capacitors are needed to balance the neutral points. Definitely, these small commutation capacitors can be put in parallel with the high voltage switches directly, so they become as a snubber capacitor. Fortunately, as we only operate the high voltage switch at the low switching frequency, the switching loss from the snubber caps can be very small. The entire three-phase operation of the HMMC is shown in the top right corner. Based on the switching state of the high voltage switches, the chain link arms are either connected across positive DC bus and the neutral point, or across the neutral point and the negative DC bus. At any moment, the DC bus is fully supported by 4 arms. As the HMMC arm output voltage are different, the current allocation of the arms are different as well in order to balance the arm energy. There are many arm current allocation options due to the freedom of the circulating current. As mentioned before, the selection of the arm current needs to make the total neutral point current zero all the time and ensure a smooth transition between upper arms and the lower arms when toggling the high voltage switching state. In our study, a trapezoidal arm current is proposed for smooth transition and zero total neutral point current, and also the constant total DC current. As shown in the simulation result, the sum of the neutral point current can be controlled at zero all the time, and sum of the DC side bus current can be controlled as a constant DC value. Following the similar principle, the Type 2 and Type 3 HMMC operations are shown in the page. Again, the 4 high voltage switches switching states are toggled based on the AC output voltage polarity. For HMMC2, when AC voltage is positive, the upper arm is connected on the AC side to synthesize the AC voltage, and the arm current is the phase AC current. The lower arm is connected between the neutral point and the DC bus to support half DC voltage. The duties will be switched between 2 arms when the AC voltage changes the polarity. Similarly, for the HMMC3, when delivering a positive AC voltage, the upper arm that is tied to the positive DC bus will be connected to the AC side and synthesize the AC voltage. The lower arm is connected between the neutral and the negative DC bus. When AC voltage moves to the negative region, we just swap the duties of two arms. An interesting point that I like to mention is during half cycle, the arm current will be the same as the AC current for both types. The difference is that at the unity power factor in the HMMC2, the arm voltage and current will reach the maximum value at the same moment. All high voltage switches in HMMC2 and 3 operate at the line frequency, and the maximum arm voltage is half of that in the MMC solution. Now let's make a comparison between HMMC and MMC and see the potential benefits. The first one is to compare the number of switches in the system. To make a fair comparison, we created 3 operation conditions based on the AC output voltage level, which are the 6.9 kV, 13.8 kV, and 23 kV as the line-to-line RMS voltage. The phase current is set as the 250 amps, and the phase shift angle between voltage and current covers the entire range. We assume the highest modulation index with the third harmonic injection. The MMC submodule voltage ripple is set at 10%. Based on these comparison conditions, we chose 2 types of IGBT devices. For the MMC submodules, we used the 1.7 kV IGBT devices and the 6.5 kV IGBTs for the HMMC high voltage switches. Based on this, we can see the number of switches comparisons in the bottom chart. It clearly shows that the low voltage IGBT numbers can be reduced by 50% due to the elimination of 50% MMC submodules in the HMMC solution. And the number of high voltage IGBT is very small in all 3 conditions. Therefore, the total number of the devices can be reduced by over 30%, leading to a huge cost savings and reliability improvement. The secondary item for comparison is the total capacitor requirement, as it determines the footprint of the system. The total capacitor value is calculated by the arm energy variation, allowed capacitor voltage ripple, and the average capacitor voltage level. We need to insert enough capacitor in the system to absorb the arm energy and the ripple limit. The top figure shows the polar plot of the capacitor value versus the phase angle. The vector length represents the capacitor values, and the polar angle represents the phase angle. Blue curve shows the MMC capacitor requirement over the entire phase angle range. It clearly shows that HMMC type 1 just needs almost half of the capacitor required in the HMMC throughout the entire range. For the HMMC2, it requires a very large capacitor at the unity power factor. This is because for HMMC2, the entire arm, either the upper arm or lower arm, is connected in series with the AC voltage and also carry the entire phase current. So there's no way to inject the circulating current to help reduce the energy level. Therefore, the arm energy variation is large. However, the capacitor requirement in the HMMC2 will reduce to 50% capacity required by MMC at the 90-degree phase shift. So it means that HMMC2 can be a candidate for STATCOM or reactive power compensator devices. HMMC2 can also be modified a little bit to easily handle the DC short circuit fault, which I will now dive into the details. So it can be a good candidate for the reactive power applications. For the HMMC3, it shows also 50% capacity reduction at the unit power factor. So it can be also a good candidate for delivering the active power. As the arms in the HMMC3 are tied to the bus, either the top bus or the negative DC bus. So the insulation design is easier, and there are other ways to be used to further reduce the capacitor levels, which also I will skip that part of discussions. So the time domain arm voltage, arm current, and arm energy at the unity power factor and the pure reactive power factor are shown below in these 2 figures. It clearly shows that HMMC1 provides a much smaller energy variations at all conditions compared with the HMMC. This means the total capacitor needed in the HMMC1 can be reduced by almost half, leading to footprint and cost savings. Lastly, we like to see the power losses. So we basically went over the loss calculation, and the results are shown in this page. Again, as we reduce the total number of devices and use high voltage switch to replace large number of low voltage switches, we can also capture the loss saving in the HMMC solution. If using the HMMC1 to compare with the MMC benchmark, we can remove over 30% semiconductor losses over the entire operation range. This improves the efficiency and reduces the cooling cost. As a summary, this table shows the high-level comparison. If we put MMC as the benchmark and all the values, including number of devices, total capacitor value, arm current, and device losses, are used as the base number, the corresponding values in the three types of HMMC are shown in the table. So HMMC1 shows 0.5 pu capacitor, 0.98 pu arm current, and 0.68 pu total device losses. The number of low voltage devices is reduced to 0.5 pu, and only 2.2 pu high voltage switches are needed. Therefore, HMMC1 has the best performance in general, but HMMC2 will show interesting benefits at the reactive power applications, and HMMC3 will show more capacity reduction through other techniques. Due to the limited space, I will not mention here in details. So in short, HMMC1 can reduce 30% devices, reduce 50% submodule capacitors, and reduce 30% semiconductor losses. Just look at the commercial MMC product. It will be a big deal of removing one of the two MMC cabinets. One more thing, as we can toggle the 4 high voltage switches, so we can basically modulate the total voltage applied to these two arms. Therefore, we have more ways to control the MMC submodule capacitor ripple at the low speed, high torque conditions. More work will be performed on this specific topic for the medium voltage drive applications. A HMMC low voltage proof of concept prototype was designed and built in CPAS. The bus voltage is set at 400 volt, and the AC voltage is 180 volt, phase to neutral. The arm inductor is 3 mH. Each arm contains 3 MMC submodules, of which the voltage is controlled around 70 volts. Each MMC submodule contains a 1.3 mF low voltage capacitor. So this proof of concept hardware prototype was used to verify the control and operation of the 3 types of HMMC solutions. This page shows the experimental results of a single-phase demonstration. 3 types of HMMC are verified. The bottom waveform shows the arm voltage change when the AC voltage toggle the polarity, and the total arm voltage can be reduced to only half of the DC voltage value. The MMC submodule capacitor ripple is shown as well. At the unity power factor, HMMC1 shows the smallest ripple, and HMMC2 shows the largest ripple. HMMC3 shows similar ripple as the HMMC1. These experimental results basically verify the feasibility of the HMMC operation and the MMC submodule reductions. The modeling of HMMC is another topic. Due to the limited time, I will not go over the details. The overall modeling process is similar to MMC, but the 3-level structure can be modeled as a square wave voltage source, which is the input to the 2 chain link arms. The decoupled average model can be established as well. One thing I want to mention here is, as the square wave voltage source contains the fundamental AC voltage, and the total AC output is produced by stacking the arm voltage on top of the square wave. Therefore, the 3-level structure can deliver part of the total power directly from the DC side to the AC side without going through the MMC submodule capacitors. This is why HMMC can save the total capacitor requirement. In addition, as just mentioned, the AC output voltage is created by stacking the square wave with MMC arm total output voltage. Compared with MMC, although HMMC arm creates half number of the voltage levels, the total number of the voltage level on the AC side is the same. Therefore, HMMC will deliver the same AC output quality as MMC, without need to change the submodule switching frequency. This page shows the high-level control structure of HMMC. It's similar to MMC control solution. The DC content of the circulating current is used to control the total arm capacitor voltage level, and the AC content of the circulation current is used to control the energy balance between arms and phases. The major difference here is that a control reference will change according to the switching state of the high voltage switches. Special controller with better tracking performance is needed to control the current references with large contents of high order of harmonics, like the trapezoidal arm current, is shown in this page. So this page shows the HMMC operation in a three-phase setting. The top waveform on the left are the AC current delivered by the converter, showing a very small level of harmonic contents. Due to the trapezoidal arm current allocation in each arm, the waveform in the middle shows the measured DC side current delivered by each phase. The sum of the current is the total DC side current, which is a constant value without major ripple. The neutral point current of each phase is measured and shown at the bottom of the figure, and the sum of the total neutral current is small around zero. Therefore, there is no need to put large split capacitors on the DC side. The figure on the right-hand side shows the arm energy balancing control performance, and the capacitor voltage in upper and the lower arms can be controlled equal to each other when enabling the energy balancing control by controlling the circulation current. At this point, we just discussed the concept of HMMC based on the three-level AMPC structure. As we know, flying capacitor is another three-level solution. So the question here is, can we apply the similar idea and create a flying capacitor-based three-level HMMC solution? By following the same concept, we can create a new HMMC topology, of which two of the switching devices are replaced by two chain-link arms. We can still call them the upper arm and the lower arm. Similarly, when we deliver a positive AC voltage, we turn on Q1 and turn off Q2. Therefore, the upper arm is connected between the positive DC bus and AC terminal. The arm current is the same as the AC phase current. The lower arm is connected in series with the flying capacitor between the positive and the negative DC link. As the lower arm is completely decoupled from the AC side, a circulating current can be allocated to charge or discharge energy in the lower arm. When the AC output voltage flips the polarity, we turn off Q1, but we turn on Q2. The lower arm will then be connected between the negative DC bus and AC terminal, and the arm current is the AC phase current. The upper arm is in parallel with the flying capacitor, and a circulating current can be created to charge or discharge the arm in order to balance the energy. So the basic principle shows that we can operate a flying capacitor-based HMMC to deliver required AC voltage and current, while has the freedom to balance the arm energies within a line cycle. As the flying capacitor voltage is half of the DC link, the maximum arm voltage can be reduced to half of the DC voltage. Therefore, the flying capacitor-based HMMC also eliminates 50% of the MMC submodules. The left-hand side picture in this page shows the arm current and arm voltage, as well as the current flowing through the flying capacitor. As discussed before, during half cycle, the arm voltage needs to synthesize the AC voltage, and the arm current is the phase current. On the other half cycle, the arm voltage is clamped around half DC link voltage, but the current can be free to allocate in order to balance the arm energy. So the total current flowing through the flying capacitor is also an AC current, so the flying capacitor energy can be balanced as well. The right-hand side shows the arm power and arm energy variations in comparison with the MMC solutions. It shows about 50% energy reductions, which means that the total MMC submodule capacitors can be reduced by 50%. However, if we consider the flying capacitor, the total capacitor reduction is about 25%, but flying capacitor-based HMMC solution require less switching devices. We only need to put one PU high voltage switches there to construct the circuit, so it can further reduce the cost. In addition, for the flying capacitor-based HMMC, we don't need to put any DC-link capacitors to operate the circuit. So this page shows a medium voltage high power AC-DC converter simulation based on the flying capacitor-based HMMC solution. The DC-link voltage is 10 kilovolts, delivering about 450 kilowatt power to a 4.8 kV AC output. The flying capacitor value is set around 260 microfarad with the 5 kV operation level. Each arm consists of 5 MMC submodules, and each module has a 1.1 kV DC internal capacitor. So you can see the total arm voltage only needs to cover half of the total DC voltage. The simulation results are shown in the bottom. The left side shows the AC current, DC side current from each phase, and also the upper and lower arm voltages in phase A. The arm current is shown on the right-hand side, as well as the MMC module capacitor voltage variations. The flying capacitor voltage varies with less than 200 volts ripple on the 5 kV average value. So this simulation result shows the feasibility of this flying capacitor-based HMMC converter. HMMC definitely shows the benefits in the medium voltage applications. The question here is, can we put HMMC for HVDC and compete with the MMC? The first thing we need to do is to eliminate these two DC-link commutation capacitors, which is hard to implement in the HVDC system. As I mentioned, we can move the caps and put them in parallel with the high voltage switches as the snubber capacitors. Then the rest of the problem is how to construct a high voltage switch with the voltage rating over hundreds of kilovolts. As the device only operates at the fundamental frequency, so we can put large snubber components for device balancing. The major question here is what type of devices should be used? The first option is the wire bonding type IGBT modules. The benefit is the low cost and low risk of supply chains, but stacking such modules in series to hundreds of kilovolt level might need some more study on reliability and failure mode as well as the protections. But technically it's possible. Other options are the press pack IGBT and IGCT solutions. It can reduce the challenge to stack devices for high current and high voltage, but we have a limited vendors to supply such devices. The third option, which I like to put a question mark here, is in the near future, we might be able to put wide bandgap or ultra wide bandgap devices and leverage the high blocking voltage capability. For instance, 10 kV or even 20 kV device can be used to reach high voltage with much less number of modules in series. So I'd like to leave this question to the audience for more discussions. So here we have a special case. We know it is hard to construct a high voltage switch with hundreds of kilovolts rating, even running at the line frequency. So the idea here is, if we operate the converter in a unidirectional mode, which means it only delivers power from AC to DC side, we can replace the high voltage IGBT switches by the simplest and the most robust semiconductor device, diode. As such, we created a new rectifier solution, namely the hybrid modular multi-level rectifier. There are many advantages. It can deliver the same AC output power quality as MMC, leading to small filter size. It eliminates 50% MMC switching modules in the system. Not like ILCC solution, the high voltage diodes commutation process doesn't rely on the AC grid, so it can operate at the weak grid without commutation failure concern. The efficiency can be much higher due to the use of high voltage press pack diodes. The total system footprint can be reduced a lot. Then the major question that needs to be addressed in order to apply this to HVDC application is, can this solution operate at different power factors so it can even deliver the reactive power to support the grid? Fortunately, we found that this converter solution can do that job. By applying a control solution, we can let the HMMR even deliver some amount of reactive power to support the grid. This page shows a 200 kilovolts, 200 megawatt HVDC simulation case. The left-hand side figure shows that HMMR can deliver different reactive power while maintaining the active power control. And the right-hand side shows the active power ramp-up process to deliver the power to the HVDC grid. Due to the limited time, the detail of this converter operation and control design will not be discussed here. This page shows the HMMR proof of concept demo by using the hardware I described before. It shows a similar performance like arm voltage, AC voltage compared with HMMC. As diode is very easy to be stacked up for high voltage, HMMR can be a promising solution for many HVDC applications. The black star function of HMMR is also possible due to the stored energy in the MMC submodules. So we might be able to let HMMR establish the AC voltage without transferring the power. We will perform further study of the black star capability on this solution. All right, let's summarize what we have covered. We started the discussion with MMC, and MMC can be considered as a two-level based chain link solution. Then we modified two conventional three-level topologies, AMPC and flying capacitor converters, and created a family of three-level HMMC and HMMR solutions. So the next question is, can we apply the same idea to a five-level structure, like a five-level AMPC? The answer is yes. If we consider a 24 kV DC voltage, then each arm in the five-level HMMC only needs to provide 6 kV output. CPAS recently developed a 10 kV silicon carbide MOSFET-based MMC submodule, which can deliver a 6 kV output. So it means that we just need two of such modules in each phase to construct a 24 kV medium voltage converter, which delivers a high fidelity AC output. All the high frequency switching actions can be pushed to these two silicon carbide MMC modules per phase. So here I will make a suspense. As we are patenting the solution now, so I will now show the circuit here. If you are interested in this, please join our consortium to learn more about it. The summary table is shown here. Both three-level HMMC and the flying capacitor-based three-level HMMC shows a promising benefit compared with MMC. Five-level HMMC can further push the power density and efficiency. So in the next session, I will talk about the modular high-frequency solid-state transformer. Solid-state transformer is a popular topic recently. Some people name it as electronic transformer, power electronics transformer, etc. It uses the solid-state switches to create a high-frequency flux onto the transformer while delivering the power. In such case, the maximum flux density can be controlled at the smaller magnetic cross-section. SST concept is not new. Power electronic industry has been doing such work for many years. For example, the first Apple computer used a line frequency transformer to charge the computer electronics. After several decades of design optimizations, the transformer right now in the latest Apple computer charger is extremely small. Now, the power electronic industry are doing the same idea for the EV charger and push the power to hundreds of kilowatts. Large line frequency transformer is being replaced by a small onboard charger with a high frequency transformer in it. And in the near future, we might be able to replace the distribution and even transformation transformers by the high frequency solid state transformer solutions, so we can enable electronic grade. SST can be also designed as a building block and enable the magnetic coupling approach to reach high voltage and high power. There are many topologies available to build such modular SST. Here I will now cover these discussions. CLC topology, as shown in the figure, can be a good candidate. It's basically a resonant converter and offers ZVS and close to ZCS for all the switching switches for minimal switching loss. It also delivers sinusoidal current to the transformer, which maximizes the efficiency. With such a building block, we can parallel and stack for higher power and higher voltage. There are two ways to control the CLC resonant converter. The first way, and also a traditional way, is to operate it as a LLC converter. Therefore, the receiving side is treated as ISR rectifiers. It's simple, but actual DCD circuit is needed, and it's hard to operate at the bidirectional mode, as the control needs to swap the gating functions when power flips the direction. Another way to control the CLC converter is to apply exactly the same signals on two sides. We name it as the dual-active synchronization control method. Such method is very simple, and no additional sensors are needed, and can operate under bidirectional condition naturally. However, the ZVS source switching of all switches are not the same as LLC converter. So the question here is, how can we maintain ZVS on all switches and various power conditions? So this page shows a simplified CLC resonant converter. We replace the high-frequency transformer by three inductors. They are the magnetizing inductor in the middle and two leakage inductors on two sides. And on the right-hand side, it shows the key waveforms in one switching period. The top waveform is the voltage measured across the device drain source terminal, and the bottom one shows the three currents measured on the three inductors. So during the T0 to T1 period, most of the power is transferred from sending to the receiving side. And from T1 to T2, that's the short daytime period. We want to make all the device finish the voltage transition and achieve the ZVS. Ideally, we like ZVS happen on all switches on both sides. The voltage transition during the daytime is mostly driven by the three current shown in the bottom. So now let me show you two non-ideal voltage transition results during the daytime. At the very beginning of the daytime, if assume two currents that flow through the leakage inductors share the same direction and is from the left-hand side to the right-hand side. According to the device voltage transition operation principle in a phase lag, the left-hand side two devices will start a voltage transition immediately as the current is flowing out of the phase lag. However, at that moment, because the right-hand side current is flowing into the phase lag, the device will be clamped by the anti-parallel body diodes and cannot start the voltage transition process. Then daytime losses are created on that phase lag until the right-hand side current flips the direction at the TA moment. Then let me show you another example. If two leakage currents now flows from the right-hand side to the left-hand side, then the right-hand side devices can start a voltage transition at the very beginning of the daytime, but the left-hand side devices will be clamped by the body diodes, therefore daytime losses are created. This operation stops until the left-hand side current flips the direction at the TA moment. So both cases are now considered as the optimal voltage transition operations. The conclusion here is, at the beginning of the daytime, if the currents on both sides of the transformer are in the same direction, either positive or negative, you will now achieve the optimal device voltage transition because additional daytime losses are generated. In addition, it potentially can create partial ZVS that produce more switching losses and EMI issues. Also, large current readings might happen during the daytime. So with the previous discussion, we learned that if we want to minimize the daytime loss, we have to start device voltage transition at the same time on both sides. Therefore, we need to meet the first design criteria. At the very beginning of the daytime, the currents on two sides of the leakage inductors have to be in the opposite direction, and both have to flow into the magnetizing inductor. With that, we can start the device voltage transition at the same time without additional daytime loss. Then, to achieve the optimal switch voltage transition, we have to make the devices on two sides finish the transition process at the same time at T2 moment. Otherwise, additional daytime losses will be created toward the end of the daytime. To achieve this goal during the entire daytime period, the ratio of the total discharge energies delivered by the two leakage inductors should follow the ratio of the device output capacitance from two sides. Then, it comes with the second design criteria. By meeting these two design criteria, it will make the device start and finish the voltage transition at the same time, thereby achieving the optimal voltage transition process and the ZVS for all the switching devices. However, the key point that I want to mention here is this design process has to be tuned at the full load condition rather than the light load case, because at the full load, the current that flows on both sides of the leakage inductors during the daytime can reach the maximum level. This large current can change the current direction on both sides. So the switching frequency and daytime need to be tuned at the full load condition in order to achieve ZVS over the entire power range. This is very different from the traditional LLC converter design, as the energy that is used to discharge the switch output capacitance is from the magnetizing inductor, regardless of the power level. However, in the CLC converter, the ZVS operation is determined by the leakage inductor current, which is highly related to the power level. Due to the limited time, I cannot dive into the details of the optimal device voltage transition discussion. like showing the detailed circuit analysis, models, and equations. So here I just like to show you the high-level simulation and experimental results comparison between the non-optimal and optimal device voltage transition performance. On the left-hand side, it shows the bad design. You can see the device voltage on the bottom, that the devices on two sides didn't start and finish the voltage transition at the same time. Therefore, additional daytime losses are created. The current also shows large readings during the daytime period. In addition, there are high-frequency voltage readings created on top of the devices, leading to high EMI noises and voltage stress. However, on the right-hand side, it shows the optimal device voltage transition performance during the daytime. Both devices on two sides start and finish the process at the same moments. Therefore, no daytime losses are generated. The minimum voltage second is applied to the transformer leakage inductors during the daytime, leading to small current readings. ZVS are achieved on all the devices with very small voltage readings. So with a brief discussion of the optimal ZVS voltage transition with minimized daytime losses on all the switching devices in the CLC converter, I'd like also quickly mention another topic related to using CLC for DC-DC application. If you want to use CLC converter to connect it to a stiff DC voltage source, like a battery or another DC bus, and control the power, single-stage CLC or even LLC converter cannot do the work, because CLC converter output characteristic behaves like a voltage source. It is hard to tie a voltage source to another DC source and control the power. Therefore, we need to put additional stage with the inductor on the output so we can regulate the current. In this case, there are two options. The straightforward option is to stack second stage buck converter. It offers the benefit of large voltage regulation range. However, all the power has to run through the buck converter, leading to lower efficiency. Also, the high voltage converter will create a large DC inductor and large EMI noises. Therefore, another option is to adopt so-called partial power processing solution. In this case, we only need to build up a low voltage regulation stage and connect it in series with the CLC output. In this way, we can let majority power go through the single stage CLC converter, leading to higher efficiency. A partial power will pass through the two stages, but the converter will be a low voltage design with a small DC inductor. This partial power design can be applied to the voltage variation less than 50% of the total DC voltage. So this page shows a design example of adopting the partial power processing concept for a bidirectional charger system. The detail of the circuit topology is shown in the middle of the circuit. This charger is rated at 18 kilowatts average power and 25 kilowatts peak powers, with a 500 kilohertz transformer in the middle. The interesting characteristic is that the converter has to regulate the voltage between 315 volts to 450 volts. So in this case, we designed a single-stage CLC converter with 375 output, and then we just need to build a 70 volts two-stage low voltage regulation converter and connected that in series with the single-stage CLC to regulate battery side output voltage and powers. So in this case, we can achieve very high efficiencies with 98.8% peak efficiency, and the power density can be pushed to 140 watts per cubic inches. So now let's change the gear and look at the high frequency transformer design in the SST unit. We are talking about the transformer for medium voltage applications. Therefore, it presents quite a lot of challenges as multi-variable design and optimization will play in the process. The key consideration is to balance the insulation, thermal, and power density. And several critical design aspects are shown in the picture. Particularly, I'd like to mention the insulation design aspect here. There are three voltage levels to be considered. The first one is the operational voltage. This is the voltage stress across the transformer during years of operation. The second level of voltage stress is the overvoltage or high power voltage rating. For the IEC standard, we need to apply 2 times of the operational voltage plus 1 kilovolt on the transformer for minutes. The third one presents the most challenging aspect. It is called the basic insulation level or impulse voltage level. It usually follows a 1.2 microsecond, 50 microsecond pulse voltage profile, and the transformer has to withstand that without any breakdown failures. For a 13.8 kV medium voltage application, the BIL level has to reach over 95 kV. The second design consideration is the partial discharge, as it can influence the transformer insulation lifetime. The partial discharge will be sensitive to the design geometry and insulation materials, especially at the interface between multi-insulation media. The third design consideration is the high-frequency voltage stress, which can accelerate the partial discharge and dielectric losses. This is not an issue in the traditional line-frequency transformer design. Moreover, the high-frequency voltage stress across the insulation layer might change as the dielectric material's permittivity will play a more important role than the material's resistivity properties. The rest of the design considerations are the thermal management and manufacturing process. All design variables need to be balanced in order to find the optimal design solution. So let me showcase the design considerations by using an example. In this example, we need to design a 50 kilowatt, 200 kHz high-frequency transformer unit with over 100 kV BIL level for 13.8 kV medium voltage applications. The transformer ratio is 1:1, and applied terminal voltage on both sides is 1.2 kV. The left bottom picture shows the overall electromagnetic and insulation design concept. To minimize the winding losses, the design only considers 4 turns by using this wire bundle. Each turn is constructed by paralleling 2 lead wires. 6 sets of UI ferrite magnetic cores are used to provide magnetic path. Interleaving winding configuration is applied to reduce the leakage inductance, so the low voltage side windings are split in 2 parallel coils and then are put on 2 sides of the primary windings. The entire primary side windings are insulated by the silicone plus epoxy composite solution. The low viscosity silicone are used to pot the lead wire first in order to push out air voids in the lead wire. Epoxy mixed with inorganic fillers are then applied to create the main insulation barrier. A long bar-shaped terminal is built on the high voltage winding exit to meet the creepage distance requirement. The entire insulation surface is applied with a conductive coating layer to control the E-field. Nonlinear stress grading material is applied from their winding terminal exit to the conductive shielding layer to control the E-field spreading along the horizontal axis on the surface of the bar-shaped terminal. This page shows the cross-section from the side view of the transformer. It shows the location of the stress grading materials between the shielding layer on the surface of the epoxy and the high voltage winding slot exit. As I mentioned before, the E-field usually shows a high peak value at the interface between 2 insulation medias. Therefore, stress control materials are very critical to spread out the E-field distributions. The conductivity of the material cannot be too high or too low. If it's too high, it will push the E-field peak very close to the winding slot exit side. If it's too low, the flashover might happen at the interface between the shielding layer and the stress control material layer. Both will create the higher PD and the breakdown risks. Therefore, the stress grading material are usually better to be nonlinear type, and the conductivity varies with the E-field strength. This page shows the reason to apply the conductive shielding coating on the surface of the epoxy insulations. The shielding layer is connected to the low voltage side voltage potential. Therefore, the voltage stress between 2 sides of the windings will be fully applied across the main insulation barrier, with smaller E-field spreading outside. In this case, we can effectively reduce the insulation barrier thickness, therefore improving the thermal conductivities and better electromagnetic couplings between the primary and the secondary side windings. Definitely, the conductivity of these shielding coating materials needs to be tuned to reduce the induced eddy current losses. This page shows the multiple pictures of the fabricated high-frequency transformer, as well as the modular solid-state transformer unit. On the very left-hand side, it shows a 25 kVA 95 kV BR level, oil immersed 60 Hz distribution transformer that can be easily found from outside, and our 50 kW 200 kHz air-cooled transformer with the same BR level. It clearly shows the size and weight reduction. The weight reduction can be over 20 times better. In the middle, it shows the modular solid-state transformer unit by using 1.7 kV silicon carbide MOSFETs as the switching devices on both sides. As the unit has the isolation transformer, the magnetic coupling approach can be applied by stacking up the unit medium voltage side to reach the medium voltage output. In this particular design, the entire unit frame is connected to the ground for plug-and-play installation. Therefore, large air spacing is used for insulation safety purpose. The right-hand side shows the BIL test setup and the impulse voltage profile applied to the transformer unit. In addition to the insulation voltage, SOMO is another design challenge for high-frequency, high-power transformer design. Particularly, the SOMO challenge is more severe on the windings in the high-power applications as the winding carries high current. In this example, we are designing a 2-to-1 ratio 500 kHz 18 kW air-cooled transformer with 750 volts as the input voltage. If we fabricated the transformer by following the best interleaving electromagnetic design configuration, it can be found that the winding inner layer temperature can go beyond 180 C, which is over 50 degrees higher than the outer surface of the lead wire bundles. This is due to the stagnated air pocket trapped inside the lead wire. Such stagnated air creates a thermal insulation layer, which causes the overtemperature and even the thermal runaway problems on the windings. To address the lead wire overtemperature issue, potting plus forced convection cooling can be considered as a cost-effective solution for the high-frequency transformer. Epoxy materials are popular for thermal spreading. It has the balanced thermal, curing, and viscosity properties compared with other options like thermal grease and elastomers. Epoxy can be mixed with inorganic filler of powder materials to boost the K value for better thermal performance, but it needs to check the change on the breakdown strength, viscosity change, and curing conditions. Therefore, this page shows a potted winding by using epoxy as the potting materials. The potting is only applied to the windings to simplify the potting process. As such, all the air can be pushed out of the lead wire bundle. This page shows a thermal characterization of this potted lead wire-based 500 kHz transformer running at 18 kW power. Thermocouples are embedded inside the transformer to measure the temperature. A 24-watt, 120 mm high-speed fan is put on the side to create a forced convection cooling condition. Due to the epoxy, the maximum winding temperature drops to 126 degrees, and the delta T between the inner layer and the surface of the winding is only about 20 C. So it shows a good thermal performance, but it needs a large fan on the side. In order to further optimize the cooling performance, we need to find a way to reduce the fan and optimize the airflow condition. In order to further improve the cooling performance, we can take a look at the airflow velocity around the winding surface and see if we fully utilize the airflow for heat transfer. As soon as the air hits the boundary of the winding, the air molecules near the object are disturbed and move around the winding. Aerodynamic forces are then generated between the air fluid and the object. The magnitude of these forces depend on the shape of the winding. The disturbed air molecules around the front surface of the winding will in turn slow down the flow just above them. This creates a thin layer of air fluid in which the velocity changes from free stream to zero. This layer is called the boundary layer. Within the boundary layer, the thermal transfer performance is little affected by the fan. Therefore, a good aero design will push the boundary layer very close to the surface of the winding to better exchange the heat flux from the winding to the airstream. The simulation result clearly shows a boundary layer formation in the design. Therefore, cooling duct with a turbulator design for better aerodynamic performance is very critical to improve the thermal performance. The goal here is to leverage all the airstream and mobilize the air molecules on the surface of winding as much as possible. The cooling duct design needs to consider overall layout, winding size, and positions in order to guide airstream. The tabulator plates on the inner surface of the cooling duct are used to break the boundary layer and push the airstream stick to the surface of the winding as much as possible. They also create a tubular airflow around the winding surface. With such design, multiple transformers can be put side by side with a good thermal performance. The detailed cooling duct and tabulator design are now shown here, but the simulation result shows that a large boundary layer is broken by the duct and tabulator. Therefore, all the air molecules blew by the fan can be leveraged to carry the heat flux. The simulation result shows much improved performance with smaller fan requirement. This page shows the 18 kilowatt transformer with a 3D printed optimized cooling duct for winding cooling. There are over 10-degree temperature improvement compared with the results without the duct. The fan can be reduced from the previous 120mm 24-watt fan to just a 40mm 3-watt fans. In this prototype, two transformers are put side by side, and both are cooled effectively. The power density is over 560 watts per cubic inches, a big improvement compared with the commercial high-frequency transformer solution. So in the next session, I will talk about medium voltage silicon carbide MOSFET in series and propose the hybrid active voltage balancing approach. As we discussed before, stacking up devices or modules can create a higher voltage for high power applications. However, if the device blocking voltage can be higher, we can reduce the number of devices in series, simplify the converter topology, or reduce the number of modules in stack. Therefore, the recent developed medium voltage silicon carbide MOSFET, like a 6.5 kV and 10 kV devices, offer a high potential for high power applications. This page shows you two examples. On the left-hand side, to build a 15 kV DC inverter or motor drive, we have to use complex 5-level topology with a large number of 6.5 kV IGBTs and a lot of clamping diodes to achieve that. However, by using two 10 kV silicon carbide MOSFET in series, we can simplify the solution to just a 2-level inverter. The second example on the right-hand side is the modular solid-state transformer unit. With the same idea, we can create a 1 kV to 10 kV SST block by using the 10 kV silicon carbide MOSFET in series. Then we just need two of such SST modules per phase to reach 13.8 kV medium voltage grade. Therefore, medium voltage silicon carbide MOSFET in stack can help reduce system complexities in terms of control, topology, and assembly. The most critical design consideration of device in series is the voltage sharing, especially the dynamic voltage sharing during the turn-off process. The good news of putting silicon carbide MOSFET in series compared with IGBT or IGCT is that the MOSFET is a unipolar device, so the device turn-off process is fast and consistent. The gate voltage control can precisely control the device turn-off process. Therefore, we can reduce the snubber component size a lot, compared with IGBT and IGCT, of which the turn-off process involves two types of carriers and also is slow and not consistent. However, on the other side, as we switch the MOSFET much faster, the parasitic capacitors around the devices will play an important role during the turn-off process, and can also affect the device in series voltage sharing result. The most outstanding parasitic capacitors come from the module internal layout, as all the terminals are bonded copper on the substrate. Parasitic capacitors are formed between the device terminals and the common base plate. Usually, these capacitors are not the same. Therefore, we need to pay attention to the impact from these capacitors to the dynamic voltage sharing from the series devices. Now, let's take a look at the 10 kV silicon carbide MOSFET module as an example. As discussed before, each terminal to the common base plate has a parasitic capacitor. Therefore, we can create a simplified circuit model with 3 capacitors in it. By performing a delta Y impedance transformation, we can create a new circuit model. It clearly shows that these drain source terminal to base plate parasitic capacitors are equivalent to paralleling additional capacitors with the devices. Therefore, if these capacitors are different, we can always cause unbalanced voltage sharing during the turn-off process, even we put the two ideal switches with ideal gate drivers. For medium voltage applications, we usually need to connect the heatsink to a fixed potential points to control the insulation stress. Therefore, there are different ways to do so. One popular way is to tie the heatsink that is attached to the module base plate to the AC terminal of the module. Another way is to connect the heatsink to the midpoint of DC link. By doing this, we also change the equivalent capacitors in parallel with the devices and cause different voltage sharing results. These two experimental results show the voltage sharing of two series connected devices in the same 10 kV silicon carbide MOSFET module. By connecting the heatsink to different points, the voltage sharing results are very different. Therefore, we need to pay attention to the heatsink connection scheme as well. So how can we balance the voltage sharing given the impact from the parasitic capacitors? The first but also the most conventional approach is to put RC snubber in parallel with the devices. The RC snubber basically slows down the device turn-off and let the RC component to dominate the voltage sharing. It is simple, but it also diminishes the benefit of using silicon carbide MOSFET for low switching losses. The RC snubber will have overheating problem as well, and to some extent, we need to put a water-cooled versions, which can occupy large space. Therefore, using a gate driver to control the turn-off delay time becomes a popular approach for silicon carbide devices. It also offers the possibility to control the voltage sharing in real time by introducing the voltage measurement feedback for closed-loop tuning. The principle is simple, as shown in the slides. We just turn off the device with higher DVDT or higher blocking voltage later than other devices in order to balance the voltage sharing. The question here is, can we just rely on the active voltage balancing control? This page shows a testing result of a converter that delivers an AC current. Each switch in the phase lag is built by two 10 kV silicon carbide MOSFET in series. The waveform shows the voltage measurement results of these two devices. The result clearly shows that during the half-line cycle, there's no change on the voltage balancing result. This is because when the AC current flows in the negative direction, the device turn-off happens when the opposite switch is turned on. Then the device turn-off actually happens on their body diodes. The body diodes voltage sharing cannot be controlled by the gate driver. On the other half-line cycle, when the voltage sharing occurs on the MOSFET, the voltage sharing result is also not consistent. We see smaller control effect when the AC current is small and over-tuning of the delay time when AC current amplitude is high. Therefore, we can draw two conclusions. First, device body diode voltage sharing cannot be controlled by the gate driver. Second, the device voltage sharing can be highly affected by the turn-off current amplitude, which will make the active delay time control tuning very difficult. For the second one, it can be explained that the device turn-off DVDT will be much faster at a high current condition. The required delay time to balance the voltage is small. However, at the small current condition, gate driver needs to put a longer delay time in order to balance the voltage. Therefore, active delay time control is not enough to balance device voltage sharing. So here we propose a hybrid voltage balancing approach. Let's go back and look at the voltage sharing result during the turn-off again. We learned that the parasitic capacitor difference will make two devices have different DVDT during the turn-off process, and that will cause the voltage difference. To address that, we can just simply measure the device terminal to base plate parasitic capacitor value by using the impedance analyzer. And then we can put an extra small cap to compensate the difference. Typically, this small compensation cap is less than 100 picofarad. Therefore, it won't be large and will not cause much switching loss issues. With adding this small passive compensation capacitor across one of the two devices, we can make the device voltage sharing close to each other for both device and body diodes. Then the left of the impact factor will be the propagation delay difference from the gate drivers to the two devices. Now we can add the active voltage balancing approach to let the gate driver slightly tune the turn-off delay time in order to keep the voltage balance all the time. As we add the compensation capacitor already, the tuning range over the large AC current will be very small, so it will be much easier to design the feedback controls and achieve this active voltage delay time tunings to manage the voltage balancing in real time. This page shows the gate driver design with the proposed hybrid voltage balance approach. We put a drain source measurement board with the RC voltage divider on it. This board is put across one of the two devices. We slightly change the capacitor value on the board to compensate the module parasitic capacitor difference. The gate driver has the onboard FPGA which produces the small delay time to control the voltage cycle by cycle. A programmable delay chip is added to provide down to 1 nanosecond resolution time for delay time tuning. A multiple pulse test is carried at the 12 kV total voltage. The gate driver can quickly balance the voltage over a few switching cycles. The early voltage mismatch is due to the gate driver internal propagation delay, but quickly compensated by the control itself. The control also records the delay value, so in the future operation, the gate driver will start with the recorded delay time, so device will not see any voltage difference during the operation. So this page shows the AC pump back test used to verify the proposed voltage balancing approach under the AC operation. The middle plot shows the experimental results without applying any voltage balancing approach. The top waveforms show the drain source voltage measurement across two series connected MOSFETs. It clearly shows a large voltage difference between the devices. When the turn-off happens on the device body diodes, the voltage difference is constant and is not affected by the gate driver and AC current. In the other half of the line cycle, when MOSFETs are turned off, the voltage sharing results varies with AC current level. On the right-hand side, it shows the test result with the proposed voltage balancing approach. The voltage across two series connected devices are controlled very close to each other during the entire AC period, indicating an effective performance. As a summary, the bottom of the page shows the proposed design process. As a first step, we need to select the proper heatsink connection scheme and develop an equivalent parasitic capacitor distribution circuit model. In the second step, the module internal parasitic capacitor values will be measured in a non-invasive approach by using an impedance analyzer. Then the required compensation capacitor that can balance the equivalent capacitor in parallel with the devices can be calculated and connected across the corresponding device. Lastly, the active turn-off delay time control on gate driver is enabled to monitor and balance the device voltage sharing in the real time. By adopting the proposed voltage balancing approach, we successfully designed and built a three-phase medium voltage inverter unit. The topology is a two-level structure, and the main switch in each switching position is realized by connecting two 10 kV silicon carbide MOSFETs in series, creating a 20 kV equivalent switch. As the device voltage sharing is balanced, we can apply a 16 kV DC input to the inverter unit and deliver a 11 kV AC output directly. The power rating of this medium voltage inverter building block is 200 kilowatts. The test result of running at 16 kV DC, of which each device takes 8 kV stress, is shown in the plot. So I hope you have not fallen asleep so far, and now we are moving to the last section of this tutorial, medium voltage auxiliary power supply system. Auxiliary power supply is a very critical component to deliver the power to many auxiliary loads, including the gate driver, controller, and sensors in the medium voltage and high power conversion systems. This APS unit usually needs to withstand the full operation voltage stress, especially if it is used to feed the gate driver. Therefore, insulation design is a very important consideration. In addition to insulation, we also want to minimize the coupling capacitor value between the input and output as much as possible, as APS system usually is the main path to conduct the common noises from the switching devices to the sensors and the control system that ultimately damage the control or cause the malfunctions or false triggers. Lastly, we want APS capable of delivering multiple loads without concerns of failure modes like open circuit or short circuit. Power density should be as high as possible to ease the system integrations. Therefore, we can draw several design objectives for such APS system as shown in this page. If you look at the commercial and research auxiliary power supply design, almost all the systems utilize the transformer to offer the insulation capability. The design difference is on the transformer structure and the location of the circuits. The input and output circuits can be put on the same PCB board together with the transformer. This can offer high density but have a limited insulation capability. If input and output circuits are put on different PCBs, it can improve the insulation but it reduces the power density. There are two ways of operating the transformer, voltage-based and current-based. Voltage-based design is more common as it follows the typical design process, but the design will be difficult to supply multi-channel loads. In that regard, current-based transformer design can easily offer modular approach for multiple receiving loads. Therefore, in order to drive multiple loads, we choose current transformer-based design with separate PCBs for the input and output circuit. It offers the balanced performance between power density, functionality, and insulation capability. This page shows several examples of the auxiliary power supply system in terms of the power density and the insulation capability. In our design, we like to push the power density as high as possible while achieving a high insulation level. The basic approach here is to drive the isolation transformer in the multi-megahertz range for smaller size. Then insulation structure needs to be carefully designed to achieve a high PD-free voltage level. The topology we chose is a LCCL-LC multi-element resonance source switching converter that can provide a constant high-frequency AC current from the sending side to the receiving side. As the sending side converter behaves like a current source, multiple channels of receiving sides can be linked via the current transformer. The switching frequency adopted is over megahertz, so the transformer size can be shrinked. The primary side winding is a single-turn design, so it can simplify the installation process and maintain a high insulation integrity. The ZVS source switching can be realized by resonant component in each receiving circuit and make the system operation consistent under different number of loads. Each receiving side has its own regulator stage to regulate the output. In addition, the regulator will make the system fault tolerant. When any load has an open circuit fault, the regulator will automatically bypass the channel and keep other loads unaffected. The total power is over 120 watts in the design. It has a total of 6 channels and each channel can feed 20 watt load. A 20 kV rated high voltage rubber insulated wire is adopted as the primary side winding to link all the transformers. The most critical design is the insulation around the megahertz small size transformer. A 3D FEA simulation model is shown in this page. The transformer is winded by the receiving side wire, which is on the high voltage side. The primary wire runs through the transformer. The E field will be concentrated inside the transformer. In order to reduce the peak E field, the inner radius of the transformer has to be designed large enough to achieve a high PD-free voltage level. Some special treatment need to be applied around the secondary side winding bending part, which usually sees the highest E field. In this design, the 15 mm inner diameter can pass a 5 kV excitations. The overall transformer and winding can be modeled as a cylinder structure. Therefore, the E field can be estimated to help find the transformer inner diameter value. To achieve a high power density design at a high insulation voltage condition, we can fill the transformer with solid insulation material, like epoxy, which was introduced before. However, the E field distribution will change due to the multi-dielectric media existing in the system. As shown in the page, if we adopt such a design, the high E field will be moved from the transformer to the winding slot exit location due to the abrupt change of the dielectric constant over there. PD can easily occur and eventually damage the insulation system. Therefore, a termination solution is needed, like adding a stress cone structure, which however will affect the power density of the system. This page shows another solid insulation design approach. In this design, we wind the primary winding into a window shape first. Then the epoxy is applied on both transformer and the window formed by the primary winding. In this case, we effectively let the primary winding form a shielding layer inside the epoxy. Therefore, most of the E field grading will be concentrated inside that window area. By doing so, we successfully push the peak E field from the winding slot exit location into the epoxy. Therefore, no high E field will show in the air. This design allows us to avoid using any special termination structure while achieving a high voltage PD-free insulation. This page shows the hardware prototype. The sending side circuit is built by using a gallium nitride switches together with the surface mount resonant elements running at the megahertz. Two versions of the receiving side are built. Both designs use the same circuit with the rectifier and the regulator stage. For air-insulated version, we have a 20-watt and 5-watt versions. The 5-watt version only needs a 2 mm thick transformer, enabling a very high density and a low profile, which can be embedded onto the sensor and gate driver circuit easily. The solid insulated version is shown on the right-hand side, potted with the epoxy in the mold. This page shows the coupling capacitor measurement results on these three versions of the receiving circuits. For the air-insulated 5-watt version, we can achieve a 0.8 picofarad coupling capacitor. And for the air-insulated 20-watt versions, the coupling capacitor is about 1 picofarad. For the silicon-insulated transformer, the coupling capacitor also is controlled less than 2.5 picofarad. All of these coupling capacitors are extremely smaller compared to the commercial product. So this page shows the partial discharge test of two versions of the receiving circuit. For the air insulation version, the PD-free voltage reaches close to 6 kV. And for the solid insulation version, the PD-free voltage reaches above 16 kV peak value. For both versions, the high power test or the breakdown voltage level is over 25 kV. This page shows the final auxiliary power supply system by using a twisted pair of wire and coaxial connectors to link all the receiving loads. The twisted wire will help minimize the radiated emissions and simplify the connection process. The prototype developed at CPAS is much smaller compared with the commercial products. Alright, I have finished all the main tutorial discussions. So this page can be considered as a wake-up call if you already fall asleep. Back to the infrastructure discussion in the very beginning. Why do we want to use high-frequency power electronics in the high-power areas? Because we see the booming of information technology by pushing small electronics operation in gigahertz range. We also see the very successful story in energy and size saving in low-power electronics area by running hundreds of kilohertz to multi-megahertz. We are now embracing the booming of medium power electronics running kilohertz in electric vehicle and electric airplanes by using high-frequency power electronics. So we want to continue that journey with the help of the wide gap power semiconductor devices and packaging technologies into higher power and higher voltage areas, and ultimately to the entire power grid. Last but not the least, I would like to thank all the faculties, students, and my past colleagues who contributed to this tutorial. Thank you all for your attention. Stay safe and enjoy the CPAS conference.